All right, we're going to start talking about uniform circular motion or objects that are moving in circles. So far we have talked about the different types of forces, but everything we've talked about has been moving along some sort of surface in what we call one dimension. So all along the x-axis mostly, a few things here and there along the y-axis. Okay, so let's look at these objects and which of the following are accelerating. So take a minute and look here. There are three ways we can accelerate, and they are all shown in these examples here. Four of the five animation or GIFs, sorry, it's late. Five of the GIFs have acceleration. One of the three we've talked about. So the three types of acceleration we have talked about are something that's speeding up. So we see that with the guy on the little roller coaster, at least at the beginning. The little boy is speeding up at the beginning. Then we talked about it being slowing down, which the little boy goes from speeding up to slowing down. The hamster is slowing down. And of course, the guy on this little cart thing, that little roller coaster thing, he shows times when he sped up, when he slowed down, sped up again, and then constant velocity. The turtle, and I am not sure what is on that turtle's back, are moving at constant velocity. So that one is not accelerating, okay? The third type of acceleration, the one that people miss the most often, is a change in direction. So we see a couple of them changing directions here. The man, when he falls into the pool, changes direction. And then down here at the bottom, the guy running through this circled track, he is accelerating because he is changing his direction. Okay, so we're going to look at a series of examples today of uniform circular motion. So there's a couple of things, there's at least one thing I need you to prepare first. So you are going to need a piece of paper. If you don't have one in front of you already, pause the video, grab a piece of paper. We're going to make a foldable. It can be notebook paper. If you have some colored paper and you want it colored, you can make a colored one, or just a piece of copy paper. Whatever paper you have is fine. Okay, so uniform circular motion. What we're looking at today is what is it and why does it happen? Okay, so those are our goals for today. What is uniform circular motion and why does it happen? All right, so you're going to need a piece of paper to make your foldable. I already told you that. You are going to need to do the hamburger fold or fold your paper in half from top to bottom and then fold it in half from side to side so that you end up with 4 equal squares on each side of your paper for 8 squares total. I believe it's the same foldable we did for the Meet the Forces. So 4 squares on each side. Okay, so in one of the squares, we're going to answer these questions. Okay, so in one of these squares, we're going to answer what are the 4 types of forces we have talked about, and how do we know when an object has one of these 4 forces acting on it, and what are the rules for drawing each of these forces. So let me open another screen here. Oh, where is my Educreations? I don't want that one. I guess that'll work. Let's go to Notability. Okay, so I'm going to open a piece of paper. Yeah, we don't need that. Okay, so we need a new note. Oh, not there. Here. Okay, so here's my piece of paper. So we have talked about 4 types of forces. It's going to be important because we're still going to be talking about these 4 types of forces. So, that's a little too bright. Okay, so the first one that we talked about was the normal force. So we called that F sub n. Okay, and that normal force, we only have that normal force if we have 2 solid surfaces, or sorry, not 2 solid surfaces, 1 solid surface. Let me erase my markings here. Okay, so 1 the object has to be on a solid surface. Okay, so if the object is not sitting on a solid surface, we don't have a normal force. And it was drawn parallel to the surface the object is sitting on. Sorry, not parallel, perpendicular. Just testing you. See if you can find my mistakes. All right, it's drawn perpendicular to the surface the object is sitting on. All right, next we talked about friction, and friction opposes motion or attempted motion. It is drawn parallel to the surface and in the opposite direction the object is moving. So parallel to the surface. The object is moving along. But the opposite direction of motion. Oops. Spelling mistake. Let me fix that. Okay, and then we talked about tension. So for tension, you have a rope, a string, a cable. And this is drawn in the direction of the push. Sorry, the pull. So whatever direction it is pulling, that's the direction you draw it in, okay? And then last but not least, we talked about the gravitational force. And the gravitational force we calculated by taking the mass of an object times the gravitational field strength. So M is mass in this case, and G is gravitational field strength. And on Earth, we said that gravitational field strength has a constant value of about 10 newtons each kilogram. We also said we refer to gravitational force as an object's weight. And we always draw it from the center of one object to the center of the other object. So whatever object is providing the gravitational force, we would draw it from the center of the object feeling that gravitational force to the center of the object providing the gravitational force, which for us so far has been Earth. So the center of the object feeling the force. Now, I know that we have written this down several times with all the different types of forces. You're going to need to use these today. So, we're going to need to have them in our notes somewhere handy. Let me see if I can make my line a little fatter. There we go. Let's try that. Okay, so let's go back to our slideshow. Let me go find it. Okay, so, oops, that was not it. It was this one. Okay, so 4 types of forces. Okay, nope, we're not there yet. I didn't put a slide for this. So I want you to add one more thing. The 3 ways to accelerate. I want that on the same foldable so you have it handy. All the information you need is in the same spot. 3 ways to accelerate. The first one is to increase your velocity. So it's speeding up. The second one is to decrease the velocity. So slowing down. And the last one is to change direction. So when we talk about circular motion, this change in direction is going to come up quite a bit. All right, let me go back here. All right, so we've talked about the 4 types of forces that we learned in Unit 2. We talked about how we know an object has one of these 4 forces. And we talked about the rules for drawing each of these forces. So we're going to do 5 different stations on the next 5 slides. I will tell you that each station is going to talk about one of the 4 forces. 2 of the stations are going to be the same type of force. So I'm going to walk you through one of them, and then I'm going to have you guys do the rest of them yourselves. So before I do that, let's talk about the foldable and what your squares should look like, okay? Okay, so let me go to a new page. All right, so on your paper, I said to make, fold it so that you have 4 squares like this, okay? So you should have a square with 4 forces. And 3 ways to accelerate. That's what you should have just written down. Okay, then you're going to have, let's do, okay, we're going to do vocabulary in one of these. We're going to do a diagram. So let's do station 1 down here. So we're going to have uniform circular motion vocab. I think that's what I called it. I got to look. And then we're going to have the equations and stuff. And a diagram. So you're going to leave those 2 blank for right now. You're going to have station 1. And then on the back of your paper, where you have 4 more squares, you're going to have station 2. Station 3, Station 4, and Station 5. I'm going to do one with you to help you out. You're going to have the same 2 things for every station. Oh, let's pick a pretty color. Let's go with pink. Okay, you're going to have the force diagram. So all of these are going to have the force diagram. And then you're going to be at the bottom, the force keeping the object moving in circular motion. You will have more space on your paper, but you're going to squeeze that in there, okay? So move that one up a little bit higher. I'm going to show you the example with station 1. So let me go ahead and put the force diagram there. And then the force down here, keeping it moving in a circle. This is written down on each slide. So let's look at what that looks like, and then we can go there. Okay, so again, for each of the 5 stations, you'll be drawing a force diagram for each situation. I'm asking that you indicate somewhere where the center of the circular path is relative to the object's position, okay? Because we're going to have some rules on how we're drawing these forces, okay? So let's look at the first one. Oh, I forgot. I put an example in here. So this is an example of what you might have in your picture. So maybe your object has a gravitational force, a normal force, and oops, sorry, jumped ahead. Normal force, and then maybe it has this tension that's directed towards the center of the circular path. So your center of your circular path in this situation is indicated by the dot. And then my diagram shows that that tension force is going towards that center of the circle. So let's look at an example. So I made videos for you guys to look at something moving in a circle. And then I gave you a picture over here to show you that's the point you need to draw the force diagram for, okay? So you're going to see a quick video, so let's watch this one real quick. Okay, so we got the little toy car. You can see it moving in a circle, okay? So we're going to draw a force diagram for this car. All right, now I said for the force diagram to draw it for the front view of the car. So that's what we're going to do, and I gave you the reference picture here in the middle of the slide so that we can do that carefully. The videos will replay. They will have, the video will go and then a slow motion repeat of the same video. There it goes. There's my slow motion repeat. So if you need to see it slow down, it will slow down for you in the second half of the video. Okay, so let's see what this looks like. So we're going to go back over here and we're going to do station 1 and we're going to draw the force diagram. So I'm going to come down here and remember we draw our force diagram with a dot or a box. We're looking at the picture here where the car is. So the center of my circle is going to be to the left of the red car at the position shown. So I'm going to go ahead and draw my X there. This is the center of the circle or the circular path. And then how many forces are acting on the car? Well, the car is on the surface or the floor. So we're going to draw a gravitational force there, pulling it down. The normal force is pushing it back up so it doesn't crash down through the floor. And then it had a piece of string tied to it. Oh, that was weird. I don't know if y'all saw that strange thing my line just did. All right. And tension is what we call the force in a string like that. So it was directed towards the center of the circle. So looking at this diagram, the only force that has anything to do with the center of the circle is the tension force. So the second question on the slide says, what force keeps the car moving along the circular path? Well, we can see it in our force diagram that it must be a tension force. So in the case of the car moving along, it's a tension force keeping it moving in a circle. Okay, so let's go here and look at another one. So the second one, there we go. Okay, so this video is a golf ball rolling around on a paper plate. So we are going to look at, maybe if it wants to work, it doesn't want to work. We're going to watch the golf ball roll around on the plate. There we go. Okay, so we see that the golf ball continued moving in a circle along the plate. So what I provided for you over here was a paper plate and a golf ball and the side view of the plate. So you can see the ball is up against a surface that's on the side of the plate. So let's go ahead and go back to our foldable and fill in station number 2. Oh, that was station 4. Where's station 2? Here it is. Okay, we're filling in station number 2 with our force diagram. So golf ball, pick a spot. Let's go ahead and pick the spot that's on my side view of the paper plate here. So the golf ball has, of course, the gravitational force pulling it down. It has the bottom part of the plate pushing it up. And then we had the plate and we had the golf ball and there's this side of the plate pushing it in. Well, that's still a solid surface, so that's going to be my normal force. And let me use a different color to indicate the center of the circle. There's my center of the circle. So looking at this force diagram, I have two different normal forces, which might get confusing. So let's call them normal force 1 and normal force 2, because remember, we do have that support force going up here. So the force for this object to keep it going in a circle is, again, that horizontal piece, or my normal force number 2. It's that wall of the plate right here that pushes in on the golf ball. All right, let's go to station number 3. So station number 3 is a flying cow. Yes, cows can fly. I bet you didn't know that, but here we go. Flying cow. So for those of you that are at home, I'm sorry. We'll be doing a flying cow lab when we get back from Thanksgiving break. I will try and take some good videos for you guys. So, okay, here's the video of the flying cow. If I go over here and look at the image is showing us where that tension is. Okay, so we've talked a little bit about this for tension forces. So let's find station number 3 on our paper. And let's go ahead and do the side view for the cow that's in the picture I provided here for you for the reference, okay? So I have my cow has gravity acting on it. It is not on a solid surface, so we're not going to have a normal force. It's not sliding against any surfaces, so it's not going to have a frictional force. And then it is attached to a piece of string, so it's going to have a tension force. And the tension force is going to look just like it did in the picture. So if we look at this picture, if we look at the video, every now and then you can see the little shiny part of the piece of string that's there. So that's a tension pulling the cow up and to the left. So we get this angled tension force. The center of my circle is over here. So if I were to do some axes here, parallel and perpendicular to the ground, so our ground for this one is the floor, I can see that I have those dreaded angles. I have a horizontal component for the tension force and a vertical component for the tension force. So my force that's keeping it in a circle is not going to be the overall tension force this time, but the horizontal component is what keeps the cow going in a circle. And I am so sorry, but I am running out of space. So circle, I'm going to go up the side. All right, it's that horizontal piece of the tension right here because that's the one that's directed towards the center of my circle. All right, 2 more stations to go. So let's look at, and I know I said I was going to make you do this on your own, but whatever, we're doing it together and it's all good. Okay, so we have not talked a lot about planetary motion. So that's what we're going to talk about right now. So here are 2 different gifts because obviously I can't get into a rocket and fly into space and record something like this for you from way out in space. So we got to look at the gifts here. And so both gifts show planets revolving around the sun. So we can pick any of the planets here that's revolving the sun. We're always doing stuff with Earth. So let's go ahead and do something that's not Earth. Let's do Saturn, okay? All right, so my force diagram, I'm going to look at Saturn, okay? There's my Saturn with the rings. And here's my sun, okay? So we've talked about this gravitational force before. And the gravitational force is always from the center of one object to the center of the other object. So Saturn feels a pull from Earth, and the Earth feels an equal pull back from Saturn. So my force diagram for Saturn, let's indicate we are doing this for Saturn, is one force, the gravitational force. So we've talked about what's the minimum number of forces an object needs to have acting on it in a force diagram. It's just one. It's the gravitational force. The center of my circular path is going to be the sun because, center. I'm spelling wrong now. Because everything is revolving around the sun. The sun is at the center of that circular path, okay? If we were going to draw a force diagram for the sun, the force diagram would go back this way, okay? Now, the sun is not moving along a circular path, so we wouldn't talk about that being a uniform circular motion, but the rest of the planets are moving in uniform circular motion. Okay, so obviously what's the force that is keeping this moving in a circle here? It's the gravitational force. So the gravitational force keeps Saturn in orbit. We call that an orbit, okay? That path that Saturn is following. All right, let's do number 5, last but not least. Oops, and I went the wrong way. Okay, we have some cars here. I tried to find 2 different examples, and they're going around a curve. So you can kind of see the cars are sliding out around that curve. So let's talk about what's going on with the cars. Okay, so the cars are going around in a circle. They are on a surface and they are being pulled on by gravity. So let's go ahead and put my normal force going up, my gravitational force going down, because the gravitational force should go down to the center of the earth, which is underneath the cars directly. And then the normal force is pushing them straight back up. They are on a level surface, so that normal force would be level to that surface or back up. Okay, now if any of you guys are NASCAR people, yes, technically I know there is some angle to the racetrack. Let's pretend there's not an angle to the racetrack. Let's pretend the road are level and horizontal, because angled tracks, we will talk about that, but they change things a little bit and complicate things, and we don't have to worry about that in honors. So let's keep it simple. Horizontal surfaces. Okay, so the car has the normal force and the gravitational force. I'm going to put the center of the circle over here. So there has to be a force that keeps those cars moving in the circle. So if my center of my circle is to the right, that means that the cars, if you look, that red and black car in the bottom GIF, you can see him sliding out, okay? You can see the red car on the top sliding as it goes around that curve. Well, we said when 2 surfaces are sliding against each other, we call that friction, okay? So the car, you can see it in the GIF, wants to skid out and go out of the circular path, and friction keeps it moving in the circular path. So the frictional force keeps the car going around the curve. Okay, so let's go back to my slideshow. All right, so we got the car going around the curves. We got the frictional force. So now you have seen an example where each of the 4 forces we have talked about contributes to uniform circular motion. So uniform circular motion is just when an object is going in a constant circle, or like a one continuous circular path, or part of a circular path. So there are some things going on here. So let's talk about that in our notes up here. So we're going to be looking at this one right here. Uniform circular motion. So let's go ahead and talk about that piece. I'm going to scroll down so that I have more space to write, because it's really hard to write on my iPad. when I am writing and trying to talk to you guys. So let's talk about uniform circular motion in general. Let's kind of tie everything we just looked at together. So again, this is the square that I entitled uniform circular motion. So this is one of the two remaining squares you have that don't have any writing in them. Okay, so in uniform circular motion, we'll talk a little bit more about speed sometimes, okay? So with uniform circular motion, speed can be constant. All right, remember speed does not have a direction, so speed can be constant. So we talked about the 4 different ways to accelerate. So we can go faster or we can go slower. Well, if we have a constant speed, we are not going faster or slower. So we need to look at the third thing. The third thing was a change in direction. So uniform circular motion is a constant change in direction. So it's constantly changing direction. So it has acceleration, okay? So since it's constantly changing direction, Newton's second law is going to apply. So we learned in the last unit, or we're still working on learning, that Newton's second law means the sum of the forces, or the net force, is equal to mass times what we call the centripetal acceleration. So it's still mass times acceleration, but we have a special type of acceleration. So uniform circular motion is a special type of acceleration. And we call that acceleration centripetal acceleration. Or A with the subscript C. Okay, so A for acceleration, C for centripetal. All right, centripetal is a fancy name for center seeking. All right, so centripetal is a fancy name for center seeking. We also are going to have a special type of velocity for this one. Because our velocity is continuing to change direction. So remember, acceleration is a change in velocity. So if the velocity is constantly changing direction, then we have acceleration. Okay, so this is a special type of velocity. So we're going to call it a tangential velocity. Now, we already heard the word tangential. We drew tangent lines in Unit 1, okay? So it's just a fancy name for the velocity that's tangent to the circle at a given position. So the next set of notes are going to go in this last square right here. We're going to do a little diagram. We're going to talk about a couple of things and how to calculate some things, okay? Okay, so we're going to do a diagram. So objects moving in circular motion, obviously they are following a circular path. So we're going to just have a block here. Okay, and let's say it's moving clockwise around the circle. Okay, let's add the acceleration vector on here. So centripetal acceleration, I said centripetal means center seeking. So I forgot a step. Let's draw in a radius here. Okay, so our circle has a radius R. And centripetal acceleration, well, that means a center-seeking acceleration. So that means my acceleration is directed towards the center of the circle. So no matter where my block is, if we moved our block down to this position on the circle, then its centripetal acceleration again, would be going towards the center of the circle. Okay. So let's go ahead and write that down over here. AC is your centripetal acceleration. Let me make sure I spell it right. And then we said it has what's called a tangential velocity. So what we mean by that is the velocity is tangent to the circle. Oh, and in the direction of motion, which that one is definitely not in the direction of motion. Sorry, I hope you didn't start drawing that. Let's try this again. Tangential velocity is tangent to the circular path and in the direction of motion. I'm going to try and be better about my subscripts. Okay, so that should be a subscript of a T. So up here at the top part of the circle, that's my tangential velocity. So that's the direction of the velocity of the cart or the block or the golf ball or the cow. Any of the examples we just did, the same diagram is going to pertain to those as well. Anything moving on a circular path. Okay, so then we have some equations we can do here. Okay, so you have learned in geometry, or you've talked about in geometry, how to figure out the distance around a circle. Okay, it has a name, so the circumference. So the circumference of the circle equals the distance around the circle. So every one time the block goes around the circle, it travels a distance equal to the circumference. So the distance an object travels around one complete circle. All right, and we can calculate circumference by taking 2 pi times the radius, okay? So 2 pi r is how we calculate circumference. Well, we talked about calculating speed and velocity, and we said velocity was distance divided by time. Well, you can find the tangential velocity the same way. But now our distance is 2 pi r, or the circumference of the circle, over this capital T. Capital T is still a time, okay? But it's a special type of time called the period, okay? And the period is just the time for one complete trip around a circle. Okay, so last but not least, so now we have how to figure out the distance around a circle. That's just calculating the circumference. We talked about how to then calculate the tangential velocity by taking that circumference divided by the period. The period is just the time for one revolution or one complete trip around the circular path. Okay, last but not least is your centripetal acceleration. So The centripetal acceleration is related to the tangential velocity in that we can find the centripetal acceleration by taking the tangential velocity squared and dividing it by the radius. Okay? Okay, so I feel like we threw a lot at you here. For your practice problems today, we're just going to do some review on tangential velocity and centripetal acceleration. And then you're going to do some questions over which force is providing what's called the centripetal force. We don't really call it that. It just means the net force towards the center. So the notes for this, your foldable, upload your pictures of this to the assignment. And then you will do the practice problems, and you need to upload photos of your practice problems when you complete those as well. If you have any questions, please let me know, and I would be happy to answer them for you. You guys have a great day, night, wherever you are at in your day. I hope you have a good one. Talk to you soon.